Welcome everyone, and thanks for coming. This is PerfView, the ultimate .NET performance tool. And I just had to put for free on this slide because, as Windows and .NET engineers, we're probably used to a lot of commercial tools which seem kind of useful, but then you figure with the licensing costs, you just can't use them in all your environments. So this is genuinely a very cool tool, which I've been using for my own production work for many years. And it was originally built by Microsoft engineers, used for diagnosing very complex issues with their own applications. And even though I'll be showing you lots of examples of .NET apps running on Windows and how you can diagnose issues with them using PerfView, it is also very relevant for other languages on Windows as well. So if you have a C++ app on Windows, you can also profile it using PerfView. And in fact, it looks like PerfView, the authors anyway, they have these grand designs to bring PerfView to other platforms as well. So there's work in progress on bringing PerfView to Linux, for example, and all other crazy ideas like that. So anyway, just to introduce myself for a moment, my name is Sasha. I work for an Israeli training and consulting company called Sela. And so most of my work over the last 11, 12 years at Sela has been around production performance investigations, diagnostics, debugging various issues. So most of my work is either working on tools to diagnose issues with applications or helping customers solve actual issues. And then, once there's a useful tool that I can apply to my production work again and again, it's an obvious fit for me to tell people about. So that's what we're going to do for the next 50 minutes or so. If you have any questions, feel free to just raise your hand, or you can wait till the end, whatever you'd like. I'll be here tomorrow as well. I'm doing workshops, so I'll be delighted to chat with you if you'd like. So just to sort of clarify where we are on the spectrum of different performance-related things that we'll be touching on in this talk. So first, on the top, there's performance metrics and simulations, the sort of work you do when starting a project or identifying issues with an existing system when you're asked to do performance work. So we'll not be doing any of that. I'm just going to assume that we know what kind of performance metrics are important to us. Could be very specific things like CPU usage or memory usage, or higher level stuff like response times from our web services, but this is out of scope for us. Then we have profiling work done in development, and this is already where PerfView can be useful. So PerfView is a tool that you can use to do development time profiling. So you write some code, and then you run it, and you measure, and you improve, and you compare. That sort of work PerfView can definitely help you with. Then we have performance and load testing. And PerfView is not a load testing tool, but it can definitely be used to analyze results from load tests and performance tests and improve the things that you see. Then we have production time performance investigations, which is sort of what I like doing. And PerfView is very useful at this stage because it's very lightweight. It doesn't require any installations. You can just copy a single executable to any production system, and you can start profiling, monitoring the system, and doing the analysis as well if you'd like. And finally, we have this sort of continuous monitoring, which PerfView can be used for, even though there's a lot of other frameworks which could be easier to integrate or more lightweight. PerfView can still be used for this as well. So you can use it to run continuously in the background and record lots of stuff. And then if there's an issue, you can go back and analyze the events that PerfView emitted and try to figure out what happened. So this is where PerfView can be helpful. So just to sort of put us all in perspective, here's an example of a production investigation that I had about a couple of years ago, actually now. And the issue was, like, the pain point introduced by the customer was that sometimes user requests to load and save files in a document management system were failing with some sort of timeout. And we suspected a lot of different components. At some point, we suspected the storage system, the network storage system, was actually at fault. And then it took us a while, like a full day, to generate a performance monitoring report, which said that the average storage latency is 5 milliseconds. And then the customer just said, it's 5 milliseconds, so clearly there's no problem. But that was the average, right? And you all know what averages are worth. So I asked for a little more detail, and it took us 3 more days to generate more specific per-minute averages. But the average of these averages was 5 milliseconds, so there were still apparently no reasons to suspect the storage array. And so at this point, my instinct is to just use a profiler. So sometimes you can just look at the metrics, and you can look at the dashboards, and you can figure out what's happening. But sometimes you really do need to bring the heavier tools in, and you need to do some manual analysis, and you need to use your brain at some point to do the analysis and not just rely on automated tools. And this is where PerfView can help. So traditional profilers, and I mean, I could just start naming vendors. There's a lot of them, obviously, for Windows in general and for .NET applications in particular. But traditional profilers suffer generally from 4 key problems, I think. The first one is invasiveness. So there's a lot of profilers which rely on some sort of code injection or binary instrumentation. So you have to rebuild your code, or you have to restart the system, or you have to inject some stuff into the system. And that's hardly OK for a production system, or it could slow you down a lot. So that's another issue. In a lot of cases, these profilers have a very significant overhead. And it's not like they try to deny it. If you look at the documentation, it could say something like, this profiler could, in some pathological cases, slow you down by 2,000%. And that's fine. It's a profiler. You're not supposed to use it in production. But no, I want to use profilers in production. I have production issues where a profiler seems to be the only option. And so I do want to actually use tools with a much lower overhead, guaranteed. We also have trace size issues. If you need to record events for, let's say, an hour until some anomaly appears, you could get multiple gigabytes of traces, tens of gigabytes in some cases, and then the profiler would fail to open the trace, and you start profiling the profiler to see why it fails to open the trace, and this is not very productive. And finally, there's licensing costs. So a lot of profilers, they have some sort of model where you can use the profiler in production and then maybe collect the data and open it on your development machine where you have the full license to the profiler. But it again complicates things. And I like to be able to just remote desktop onto a production system, run the profiler, analyze the results, and in some cases there's really no other choice than to go through that approach. So again, finally, this is where PerfView shines and comes in. PerfView is 90% a wrapper on top of a Windows framework called ETW, Event Tracing for Windows. How many of you have heard of or used ETW before? OK, so about half. I'll tell the rest that ETW is an extremely useful framework, which was introduced as far back as Windows 2000. So it's been around for almost 20 years. And it was originally designed to be a logging framework. So it's something Microsoft put into Windows so they can trace Windows drivers and the Windows kernel, so that a Windows engineer could turn on some traces on a customer system, record them, then analyze them, only for Windows components and Windows drivers. And then the whole thing just exploded in popularity because it's really, really cool. It's a high-frequency, very low-overhead logging facility, which is built into the operating system kernel. So it's not something you install or configure or have to enable. It's just part of the OS, and it's hopefully as fast as it can be. So you can write huge amounts of data through this kernel subsystem really, really fast. And generally, the way ETW works is that you have 3 kinds of components around this central concept of an event tracing session. So an event tracing session is something a controller would create. A controller could be a piece of code, could be an application, could be some sort of scheduled task. So a controller creates an event tracing session and then enables specific providers. So providers are just pieces of code, again, around the system, which write events, which generate interesting events. And there's thousands of built-in providers in Windows, plus the .NET framework itself has a ton of providers as well. And the runtime, the CLR, also has a provider with a bunch of interesting events. So there's a ton of interesting things, and we'll look at some examples. So the controller creates a session and enables certain providers to write into that session. The session can then go into files, so you can have the session record into files, or it can just record into in-memory buffers. And if it goes into a buffer in memory with no files, then of course you're going to run out of space at some point, so it's a cyclic buffer usually. So as soon as you run out of space, you start discarding old events and replace them with the new events. So this is how it works. And finally, at the other end of the pipe, you have consumers, which are, again, applications that can read events from the session or from a file. And you can do both. So you can have a session that writes to a file, and someone is then reading events from the file, but at the same time, there's also a consumer which reads events from the in-memory buffers and performs some kind of real-time analysis, aggregation, alerting, and so on. And by the way, that last fact that you can do real-time analysis of ETW events is not extremely well known. So a lot of people know that you can record ETW events to a file, but not that you can build tools which analyze them in real time. And I have a couple of open source projects which are built around this idea of analyzing the traces in real time without going to disk. And of course, for some production users, it can be a lot more efficient. You're not putting anything on disk, you're just analyzing events as they occur. Cool. So PerfView, again, is 90% a wrapper on top of this stuff. And what kind of events could be interesting for doing profiling, for diagnosing actual issues with Windows and .NET applications? So here are some examples. One very useful provider, which is part of the Windows kernel, it's built in, you don't have to do anything to enable it, is called the sample provider. And it's basically designed to fire an event every 1 millisecond of CPU time. So whatever the system is doing, you can have an event fire every millisecond, and it tells you what's currently happening. So which process is running, which thread is running, which function is running, and what the call stack is. That's actually a feature shared across all the different events. So every ETW event you can capture with a call stack that tells you where this event came from. For this specific example, it's super useful because you know not only which process was running or which thread was running, but also what the full call stack was. So you get a sample of what the system was doing at that 1 millisecond interval. If you collect a lot of these events, you get a general profile of what's happening on the system, a CPU profile. So that's a very standard approach in general, just taking samples of CPU work and then aggregating them. But here, we have it actually built into the OS. So again, it's not like a third-party driver that you need to install and it would do the sampling for you. It's just built into the kernel. You turn it on, you get the events. So that's one really important example. Another one is the CLR GC provider. So the .NET runtime has events for garbage collections starting and ending, for object allocations happening, for various other interesting GC-related things like finalizers running, that sort of stuff. So there's a ton of events in the CLR itself which can be used for interesting diagnostics. So for example, we'll see a demo of memory profiling, so figuring out where the memory traffic in your code is coming from. And that's going to be based on these events. Then we have some other stuff in the kernel which is useful. We have the context switch provider, which is an event that happens whenever there's a context switch. So there's a switch from one thread to another thread. You can use that for blocked time analysis, so that whenever you have a thread entering some kind of wait state, a sleep, wait for some lock, an IO call, you can record that, and then you can record the switch in and figure out how long that wait took. So you can profile the system not just for CPU work, but also for IO, waits, locks, and that sort of thing. And we also have a bunch of other stuff. We have IO events for file accesses, registry accesses, network stuff. It's all built in, which is, again, one of the cool things about ETW in general. It's all built in, and PerfView, again, is just a tool for recording and analyzing all of this stuff. And in fact, PerfView itself, I wish we had time to go into that, but PerfView itself is built in a pretty modular fashion where the UI that you're going to see is, again, just the tip of the iceberg on top of a library that you can integrate into your own applications. So you can build your own PerfView with a different UI or with no UI that would do analysis and generate reports and push them somewhere else. So you can build self-diagnosing apps, you can build your own profilers, and it's all open source. All right, so let's take a look at what's in an ETW recording and how PerfView can help. So ETW, again, is a tracing framework. So essentially, you are recording a lot of events, like log messages, and then you need to analyze them. So you can, let's say, convert it to a CSV, and then you can read that CSV, or you can import it into Excel, or that sort of thing. Again, not super productive. So we need tools that would record the interesting stuff, aggregate the interesting stuff, display the interesting things in appropriate ways. And this is, again, where PerfView is used. So PerfView was born, like I told you in the beginning, as an internal Microsoft project by Vance Morrison, who's an architect on the .NET team. He's done a lot of work on CLR performance, on Windows performance, and on the .NET framework, the C# stuff performance as well. And this is more or less the tool they now use for profiling and for improving performance across the board. There's, of course, other profilers Microsoft uses internally, but on the .NET team specifically, this is a very, very strong contender. Now, PerfView doesn't have a fancy UI. It's not pretty. This is more or less what it looks like. It's blue stuff on a gray background. It's yeah, and it's improving a bit because it's now open source and there's contributions from people outside of Microsoft as well. But the general theme is that the UI sort of sucks, but the functionality is what matters. So I'm going to show you some examples, of course, and let's start with a general profiling investigation. To save us a bit of time, I do have all the recordings prepared ahead of time, but I will show you the general steps, and if we don't have time to do everything live, I'll just show you the pre-recorded stuff. So this is the general PerfView window, the main window, and so there's a ton of documentation kind of built in, where there's links and you can click them and it would open a documentation window or some videos online. Vance, the author, has a bunch of stuff on recorded with a bunch of videos that you can use. The main collection features are under the collect menu. So you can either run an application and profile it, or you can collect events system-wide. So you don't have to restart your system or anything. So let's take a look at the first scenario. What I have here is this very simple ASP.NET application running in IIS locally on this machine. And it's displaying a list of speakers at some conference. And I'm refreshing the page, and there's an error, but then it goes away, the error, so don't worry about the error. However, if we do refresh the page a lot of times, then you'll notice that occasionally it is very slow to reload. So there's some random element in there, so it doesn't look, I mean, I might be making this up, but yeah. But occasionally there is one very, very slow, one very, very slow request. Now, it's actually good, that it's not reproducing now, because it's the perfect example of what can happen to you as well. So, someone is complaining that this specific page is so slow, but then there's no way you can reproduce it. Here we go. It's now taking like 5 seconds or something to come back. So this is the sort of scenario we want to profile. Why is this page taking so long to load? And if we can't reproduce it easily, then I might just say something like, let's just enable collection in the background and come back to me when you have actually reproduced this issue. So here's what you do in this case. I've actually, again, like I told you, I've ran this in advance, so we don't have to wait now. But basically what I did is just I launched PerfView start, and I told PerfView that I would like to record into a circular buffer, 512 megabytes in size. This is kind of important because this is physical memory that you're not going to be able to use at all. So it's reserved by the kernel for this tracing session. You've just lost 512 megabytes of memory for this purpose. So if you don't like this size, you can pick another size. But this is how many events we're going to retain. And we're not going to flush anything to disk yet. And then there's a bunch of other flags. And finally, there's this no view switch, which just basically tells PerfView, start the recording, but don't show any UI. As soon as you reproduce the issue, you can run PerfView stop, like I did here. However, it's still a little manual. It's like semi-automatic, but it can be improved because PerfView has a bunch of triggers as well that can be used to stop the recording for you automatically. So for example, I could set up PerfView so that as soon as we have a slow request, it would stop the recording. But then what if it happens multiple times and I'm interested in all the different occurrences? So you can set that up as well. Essentially, you can have PerfView record into this memory buffer, but when an interesting thing happens, it would flush the events in the buffer to a file and then keep recording into that buffer. So that whenever an interesting event occurs, you have the last 512 megs of events that you can analyze. So again, I've done all of that. And here's what the report looks like when you open it up in PerfView. So PerfView does a lot of unrelated things for some reason. For example, it would zip up the file for you so you can copy it over to a different system and analyze it there. This is perfectly supported and it works. But here, we're just analyzing it on the same system. So I've opened that zip file. And then there's a bunch of reports that we can open. And I could show you some, but we'll focus on one specific report first, which is called ASP.NET Statistics. And this is something PerfView just magically understands. It knows about the ASP.NET events, which are, well, specific to ASP.NET, and it has a special report just for those. And here's what the ASP.NET statistics look like. This is HTML, so it just opens like a mini browser window with the HTML report. Again, UI is not the strong part of this tool. But it says here I had a total of 58 requests, and on average, I had 1 request per second, which is not a lot. But what's interesting is that if I scroll down a bit here, so it has like time intervals. This is in milliseconds. So each row in this table is a 1-second interval. And then it has the slowest request in that interval. So it has a max response millisecond column here. And you see over here, we had like a 5-second request. We had a 5-second response, actually. So that's interesting. Another interesting table is down here, which is statistics per request URL. So if you have a lot of different pages, then of course you can get a summary per page. And here specifically, I had 29 requests to the main page, and I had 2 of them take slower than 5 seconds. I also had 2 take slower than 1 second, so it's basically the same 2 requests. Cool. So that's the statistics, right? And we know we're not making this up. There really is a problem. There are some slow requests. Let's take a closer look. So there's this extra report here called ASP.NET Thread Time with Tasks Stacks. Right, so what does it even mean? So the thread time is a general term that PerfView uses for describing the full activity of a given thread. So it's not just CPU time, it's also blocked time, I/O time, anything the thread was doing gets recorded. And it's actually done by a combination of 2 providers I mentioned earlier. So it's the samples. Every millisecond, we get a sample of what the CPU was doing. So we know what the thread was doing when it's running on the CPU. But we also have the context switch events. So we know whenever the thread is switching out and coming back, we know the duration of that context switch. So we know how long the thread spent off the CPU, say sleeping or waiting for I/O and so on. So this is what thread time means. With tasks, this refers to the task parallel library, TPL, which is a .NET parallelism and concurrency framework. And finally, stacks means we're actually going to see not just statistics, but actual call stacks. So which call stacks in the application are taking lots of time in these requests. So let's take a look at the report. I have to pick a process here, because the recording was system-wide, even though I only care about the IAS process that was running this application. So here it is, W3WP. This is the IAS worker process. And then we get the following. So we have this tree view here, and it has 2 fields for now. So it has this not in requests section and requests section. So the web server could be doing lots of background processing as well. So we could look into that too. We could see what was the server doing when it's not actually working on requests, but I only care about the requests here. So I'm gonna expand the tree. And again, this fantastic UI, you have to click the checkbox to expand the tree. But anyway, here's the request that took 5 seconds. So this column here is the duration in milliseconds we spent in this node and its children. So this is a request that was made to sdpapp.web. This is the main page. And it took 5 seconds. So now let's see what happened in that request. So I expand here. And it tells me, OK, so the thread handling that request was thread 4132. And there was 158 milliseconds of CPU time in that thread. But the total is still 5 seconds. So we know that most of the work was probably blocking for something, maybe a database, maybe an external service, but we only had 150 milliseconds of actual CPU work. Now we can keep expanding this, and in fact, as you see, it's basically a stack tree, which tells you what the thread was doing during the processing of that particular request. And you can have multiple threads involved in the processing of a single request, and that is something PerfView just magically understands. It uses some sort of activity identifier which flows across threads, so if you have multiple threads involved, they would all be aggregated under the same request. If I expand this a little, it goes through a lot of system web methods, and I can collapse this whole thing because this is the framework. I don't care about it, so I can just go right-click this, and I can say fold this module. So it just goes away. And oops, actually I want to go up here. And so now this is my code. So home controller.index, this is me. And then this is where we spent 5 seconds almost. Conference service get speakers. And we can keep drilling in. So this is actually an external service, or anyway, it simulates an external service. But this is where we spent 5 seconds processing this request. This is why we took 5 seconds to return a response. So this is, again, it was running in the background while the requests were happening. It was recording into a memory buffer. And then as soon as something interesting occurred, we just flushed the whole thing to disk, and we could analyze it on the spot. Again, it includes both CPU time and blocked time. So I/O, locks, database accesses, whatever it was the threads were doing during that request. So that's pretty nice. And I want to show you a bunch of similar examples with slightly different scenarios. So I'm going to go back to the slides for a moment. The whole tree that you were looking at, the alternating white and yellow lines and the checkboxes and everything, it's debatable if this is the best way to visualize stack traces. So PerfView just recently got flame graph support as well. How many of you have seen or used flame graphs before? Fewer than ETW. So yeah, on Windows, flame graphs are kind of still making their baby steps, but it's a super, super useful way of visualizing stack traces. Instead of looking at a tree, which you have to keep expanding like this, you just get a single interactive diagram, which you can drill in and out of as needed. And so this is a very recent addition, but PerfView now has flame graphs. I'm not even sure the official version on the Microsoft Download Center has it, but the release on GitHub already has this feature. So this is just a flame graph visualization of the same thing. And I'm not going to go into what flame graphs are exactly, but some people will definitely prefer flame graphs to the stack trees in terms of quickly figuring out which pieces of code are taking lots of time in your profile. And these can be compared as well, and there's a ton of additional features. All right, so that was CPU profiling and blocked time. Let's do something slightly different. Let's investigate application startup. And the reason I'm going there is that it's a slightly different set of events you would be interested in. So when looking at application startup performance, there's multiple factors which could be interesting. One is, of course, just CPU work. But then there's also disk I/O, which often affects the profile very, very strongly. And there's JIT compilation, right? Whenever you launch your app, There's a bunch of .NET code that has to be JIT compiled, and that can take a lot of time. So let's see what profiling startup performance looks like. So here, I'm going to use the collect mode. And this is what the collection window looks like. So let's do startup2.etl. And this is the beautiful checkboxes that you can check to specify which events you care about. So for example, there's this file IO checkbox, which is already checked. And I can also do registry accesses, and there's network as well, and background JIT compilation, and a bunch of other stuff. So I'm going to hit Start Collection. And now we need an app which is kind of slow to start, and we want to investigate that slow startup. So I'm going to launch Visual Studio. And here it goes. This is warm startup, right? So I already have one Visual Studio instance running, so it's not going to be loading a lot of stuff from disk very slowly. But here it is. Took a few seconds to launch. And as soon as I think it's kind of ready, I will just go back to PerfView, and I will click Stop Collection. And then it loses focus. This is a bug that's been around for at least 3 years. Anyways, the results are coming back. You see a progress bar down here that says we actually collected tons of events, and we are now parsing the whole thing and analyzing them briefly. So this should take a few more seconds. There we go. And the results are down here. Startup2.etl. This is what I just recorded. All right, so again, we have a bunch of these reports we could look at. So we could look at CPU time, we could look at disk, we could look at I/O. Let's see, let's maybe start from some statistics. So under advanced here, I have JIT statistics, so JIT compilation. This is based on ETW events, right? Nothing new here. It's just the CLR generates events whenever a method is compiled, and then you can figure out how long JIT compilation is taking. And PerfView simply aggregates this information. So here's the report, JIT statistics for the dev-env process. And it says here that the total CPU time for that process was 21 seconds. And during startup, we compiled 8,815 methods. And that took us 5.7 seconds. So in other words, 26.8% of the CPU time we used during startup was for JIT compilation. That's quite a lot. And let's see what exactly happened. So there's a CSV that you can export from here and open in Excel and start analyzing it. But there's also a summary here. And this summary is by assembly, by DLL. And you can see the number one after total is JetBrains Platform Shell. And the one after that is JetBrains Platform Core. And I have ReSharper Ultimate installed. And so, yeah, and there's also these two guys over here. Now let's take a look at actual numbers. So JetBrains Platform Shell had almost 1,700 methods that had to be compiled during startup, and that took us just over a second to compile. So this already means that even if we ignore I/O and loading this stuff from disk and any CPU work, I can shave off at least 2 seconds here by disabling, well, ReSharper. Or maybe not having it, do the JIT compilation on startup, It looks kind of weird. Anyway, this is interesting. Another interesting report we can get from the same place is I/O stacks. So this is based on, again, ETW events, but this time from the kernel. So we have kernel events for reading, writing, opening files, and we can see which stacks in our code were doing that and which files were being accessed. So here's a quick way of looking at it. Here's Visual Studio Process. And here are all the threads. And they had different amounts of disk I/O performed. But here's the interesting thing. I think I mostly care about the main thread, because that's the thread that's being, that's the thread responding to user input. So if the main thread is doing lots of I/O, this is especially suspicious. And in our case, here's the main thread. That's the startup thread. And this is the amount of bytes it either read or wrote to disk during startup. So that's just under 5 megabytes. And you see, most of the work was actually on a background thread. But somehow, inevitably, 5 megabytes were actually read or written by the startup thread. Now, what were these files? Which call stacks were making those accesses? We can just start expanding and drill in. This is going to be harder than the other examples because Visual Studio is a complex application, and the stack traces are going to be quite elaborate. Here's another example where a flame graph could be useful. Another way of looking at it is, well, ignore the stack traces, just show me the files. Like which files was Visual Studio reading or writing during startup. And to get that, I can just go to the by name tab, and this shows me the files. And you can see that the biggest one file was imagelibrary.cache. I don't know what it is, but 64 plus megabytes were accessed in that file during startup. Next one is Visual Studio default catalogs, config, CTM, and so on and so forth. So this is the I/O performed by Visual Studio during startup. We could do the same thing for CPU. We could do the same thing for assembly loads. So we have a ton of events which can help figure out what's happening during startup. Let me show you a different scenario. Again, just based on the same sources of instrumentation, but I think an interesting example nonetheless. So here's a CSharp app, a console-based app this time, which is a compiler. So it's reading an input program, and it's generating some machine code. And the program is kind of big. So let's see, bigprogram.jack. It's 500K almost. And so the compiler takes its sweet time, and it takes minutes to actually get through the whole thing. So while this is running, I can just quickly grab a recording. So this is more like a development time profiling session. I just wrote some inefficient code. Let's go ahead and profile it. So compiler.etl. And I will keep basically the same settings. And I will start collection. And this is going to go on for a while, so I'm not going to wait for it to complete. Just let it run for a few seconds. And then I'll stop collection. And this time, I want to show you a report we haven't seen yet, which has to do with garbage collection events. So what was happening in this app in terms of memory activity? So compiler.etl is up here. And in the memory group, there's a report, and then you can get the stacks as well. So same thing as with the JIT compilation. So the report is called JIT Stats. Let's open this one. It takes a while to render because there was a lot of memory stuff and lots of garbage collections here. The process I'm interested in is this Jack compiler, but you can see I collected system-wide, so I do have statistics for all the processes. I have to pick the one I care about, and then here's what it looks like. Total CPU time was 13 seconds. Total GC CPU time was 6 seconds. So that's, I'm not good at that. It's 46.7%. There we go. And also, it says here that we allocated like 12 gigabytes in 13 seconds. Right. So that's pretty impressive. Actually, it is impressive just in theory, right? It's kind of nice. The .NET runtime is so well optimized. You can allocate like almost a gigabyte per second, and everything is still working. Anyway, there's another interesting metric here, which is GC CPU milliseconds per megabytes allocated. I'm not sure you'd come up with that yourself, but it's an interesting metric. It basically says, how long did it take the GC to take care of every megabyte we allocated? And the result is 0.5 milliseconds. Again, I think it's not bad. But anyway, we have tons of garbage collection. We are spending almost half the time on garbage collection. And another horrible statistic is this. 21.2% of the time, my code was actually not running. So not only was there a GC taking CPU cycles, but the GC had to pause my threads, had to stop the application completely in order to do garbage collection. And the .NET GC, in recent versions evolved significantly, and more parts of the garbage collection cycle can be done concurrently with the application. But still, there's some parts that have to stop the world and stop all the threads. And in our case, it's 20% of the time. So 20% of the time, I'm not actually compiling anything. I'm just reclaiming garbage. And for a compiler, which is kind of a throughput-oriented app, maybe it's not such a big deal. But for anything user-facing, 20% pause time is not great. And also, we could maybe see what the longest pause was, which is also interesting. So here are the more specific statistics. This is GC rollup by generation. So overall, we had 3,545 garbage collections in 13 seconds. Again, it's pretty impressive. The good news is the maximum pause time was 14.7 milliseconds. That's the longest time the GC had to stop the threads for a GC cycle. But we just had a lot of these pauses, so it does add up to a lot. We also have more specific info on the sizes of different things. And there's also this table here, which shows all the garbage collection events in a table. And you can see the duration of each GC and how much memory was freed and so on and so forth. And this is mostly interesting for very low-level GC tuning, which we're not going to do now. What I want to understand is why this Jack compiler process allocated 12 gigabytes of memory compiling that little program. The program is 500K, and we already allocated 13 gigabytes, so something's fishy here. I'm going to close this report and open this one, GC heap alloc ignore free coarse sampling stacks. Right. So what that is a report showing you allocation call stacks, so which parts of your code allocated lots of objects. And it's based on coarse sampling, which is why it appears there. So basically, if you record every single object allocated, you're going to end up with huge traces, which would be probably unopenable. And it's going to slow you down probably by a factor of 10 at least. So here, we're not actually recording every single allocation. We are sampling the allocations. Basically, what PerfView is doing is it takes an event every 100 kilobytes of allocated objects. So every 100 kilobytes, boom, we have an event that tells us what object we were allocating at that moment. It's just built into the CLR. PerfView just has to turn it on. So let's open the report. Jack compiler is my process here. And it starts with this summary table showing what kinds of things we were allocating. So it says here large object is 99.9% of what you allocated. And it says large object and not the actual types because you might remember that the CLR has this concept of a large object heap, right? So the large object heap is reserved for objects greater than or equal to 85,000 bytes in size. So large object here is just that. It's anything greater than or equal to 85,000 bytes in size. That's large objects. And if I click large object, though, it will give me this tree view of where I allocated these large objects in my code. And also it tells me what the large object were. So we had string allocations, basically. Again, that's 99.9% of all the allocations in my app. And they're coming from string.concat. So I'm concatenating strings. But that's bad, of course. But where is that coming from? So we can just keep going up this reversed tree. So this is coming from here. Jack compiler compilation output textwriter.write. So this is some code in my compiler internals, which is writing compilation output. And I can keep expanding this tree, and you can see specific pieces of my code generator which are calling that stuff and doing the allocations, and so on. And in some cases, when the stars align, I can even go to source from here. Do you trust this file? I think I do. Yeah, that didn't work. Anyway, it's supposed to show you the C# source code and point to the actual line. But if your methods are small enough, you don't need that. So you'll figure out that in this method, you're doing extraneous string allocations, and you should take care of this. Right, so we have allocation profiling as well. I hope you noticed that all my demos, I wasn't actually restarting the application or changing any configuration. This is all happening in the background, and you can perfectly use it alongside your actual running process. I want to talk about one last feature, which is not really a profiling feature, but it's quite important. I only have 4 minutes, but I'll tell you the general picture. PerfView has a pretty cool capability, which is not strictly profiling, and it's not based on ETW, which has to do with memory analysis. PerfView can capture heap snapshots of your application and then show you what kinds of objects you have on your heap and what keeps them alive. So you can use it for memory leak analysis as well. You can ask PerfView to capture a snapshot of the heap and then figure out what objects are taking lots of space. Now, this is pretty cool in itself, because there's a bunch of commercial memory profilers where you have to pay for a license to get basically the same functionality, but it's even better than that, because PerfView has its own snapshot format, which in a lot of cases is like 1% of the size of what you'd get from other tools, because it has a lot of techniques for compressing the snapshot, discarding specific objects, discarding object contents, discarding garbage objects. It has a bunch of optimizations for capturing a very, very minimal amount of information, which still represents all the objects on your heap. So just as an example, if I take my Visual Studio process and I just use Task Manager to capture a dump file, which is not exactly what other profilers would do, but it's sort of the general principle. We just write out the process memory to a file. That is time-consuming, and the output, see, it's an old version of Windows, so I'd have to paste it manually like an animal. So that's 600 megabytes, a 600 megabyte dump file. All right, now if I use PerfView to take a heap snapshot, find that Visual Studio process. To be fair, let me make sure, yeah, so it's this one here, dump GC heap. So now, to be fair again, it's going to take longer, actually. I didn't tell you it's going to be faster. It is going to be smaller, though. So once it's done, oh, and by the way, the process is still running. The process is perfectly responsive. It's not frozen. You can keep working. The system keeps sending responses to users. It's all still happening in the background. And then we have the file. And the file, oops, is this from now? Yes. So it's 6.6 megabytes. It's a factor of 100 smaller. Almost. And it has all the same information. It has enough information to perfectly reconstruct what objects you have on your heap and the references between them and so on. I don't have time to show you the whole thing, but I do have time to show you just a very, very basic screenshot, just, real quick. So this screenshot here shows a diff between two snapshots, and PerfView can tell you which objects are growing in memory. So essentially, you capture multiple snapshots, and you can see which objects you are getting more and more references to in memory. So in our case, it's these two guys, memory leak response and memory leak request. And then, going back to my last screenshot here, you also get this nice reference tree that tells you what kind of references you have to these objects, so you can trace it back all the way to something called response cache, whatever, which is like an unbounded cache, which is causing the memory leak in this example. So, I didn't show you the whole process, but you can capture memory snapshots, you can compare them, and you can get these reference trees all in this beautiful PerfView UI, but still. So functionally, it's all there. So I'm at the end of my time and also of the slides. I wanted to show you that the foundation, ETW, alongside with this nice wrapper, PerfView, can be used for a variety of different scenarios, for a variety of investigations. You can actually profile things in production on Windows today with a freely available tool that you just copy to a target system, run it, record, and analyze the results wherever you want. I use PerfView almost on a daily basis for my work, for development profiling, for production profiling, for recording stuff in the background and analyzing the events later. And it's also very interoperable because it's all based on ETW. So you can record with one tool and open in PerfView. You can record with PerfView and export to another tool. There's a whole ecosystem of free tools based on ETW that you can use today. I don't have time for questions right now, but I will step off the podium to make room for the next speaker, and then you can ask me whatever you'd like, and I'll be here the whole day and tomorrow as well. Thank you very, very much for coming.